Alrighty. So today we are going to be talking about centripetal force and give a little brief explanation about centripetal force. First of all, let me go do a little refresher. So we defined the beginning of the course displacement. Displacement, which is defined by the distance traveled, which we gave it delta x. Now, what does delta mean? This little fella means change in the x position, which means it's wherever you were final minus wherever you were initial. So we're going to say this is our final position. This little fella, let me get a different color on this. And this is going to be our initial position. This little fellow be our initial position xi. And we gave it, let me actually get this I a little closer, it's a little far away. And we gave it the letter D. All right. And so this displacement that we said this is the letter D divided by T, and T is going to be for time, which that give us the velocity. And we gave it the letter V. Now the units for velocity was distance. Well, let's go. The units for distance we had as meters. The unit for time is seconds. So it'd be distance over time, so it'd be meters per second. Now, you get different color, get red. So this velocity that we get, so this little velocity, divide that by your t for the time. And that's what we had talking about is acceleration. And we gave it letter A, and we defined the units for it as meters per second square. Actually, let me go ahead and do this. Meters per second times the second for the, that looks better, which is going to be meters per second square. And the whole point of this, that we take this acceleration and we multiply it, we use it on some kind of mass. So M is going to be our mass, and we define the mass unit as our kilograms. And that gave us something called the force, which is, we give it the letter F, which is going to be your kilograms for mass, meters per second square. And we call that the Newton in honor of Isaac Newton. And we gave it a letter N as our unit for your force. Now, let's say we have an object moving to the right and we have a force on the object in the same direction. What? Let me actually, I don't like the way I wrote what. What will happen? So let's say we have an object. Let me put up a question mark. Let's say we have an object. This object has a velocity going in there somewhere with a velocity because it's moving, it has a velocity, and we apply some kind of force on it on the same direction. Now notice I put the arrows on top of these to declare that they are vectors, which we talked about that the direction matters. So what would happen over here? This will, you're right, speed up. Okay. Now what if the force was opposite direction of the velocity? So we have an object right now. What will happen? Let me just write down the question. So we have an object. This object has a velocity going inwards, but let me get a different direction, a different color for the force. And let's say you have a force going in on the other side. What would happen? Well, obviously, it will exactly slow down. Okay, so now let's do another question. Let's say, right over here. So let's say we have an object moving to the right, but the force this time is going up. What will happen? So let me go ahead. Here's my little object again. And we have it's going to the right. That means it's moving. That means have a velocity to the right. But this time we have a force that is going up. Now, what's going up means? Going up means that the force is perpendicular to the velocity. So this time I'm going to have a force going on top this way. And it's going to be perpendicular to the velocity. So what would happen in this case? Well, the object will turn. So what will happen? The object will not speed up or down. It will turn. And the object will turn. And that's what we talk about centripetal force. Centripetal force. Now, when you talk about centripetal force, it comes in from the word century, which means, and this is actually your key word, is century, which means it is for a center seeking force. Where this force is always directed at the center of the circle. So basically, in other words, the centripetal force, it causes an object to turn in a circle. So let's say we have our object again. If it's right over here, which we said that it will have a velocity. See, the velocity is over here. Let me write it under it. And is directed by a force. Now, what would happen to it? It will turn. So we'll turn, let's say up to here. Let's say if it's over here, here's our object, which means that it would have a center seeking force going in this way. And a velocity perpendicular to it, let's say going this way. And again, the object will turn. So let's say it turns and say it's over here. Same thing. We'll just have a velocity, let's say this way. And it will be perpendicular to the force. It goes over here. Here's our object. And no, I didn't change color. Again, we will have a force going in, pointing inwards. And a velocity perpendicular to it. And again, we'll come back in a circle. Now we keep on going back and forth till when? Until, again, according to Newton's first law, until you have a force that stops it, slows it down, or like a friction, or accelerates it. Now, so this force that we talked about, we said it was equals to mass times acceleration, if you remember from the beginning of our lecture. So our force was mass times acceleration. So the mass of the object times the acceleration. We defined the acceleration as velocity over your time. So that means our force is going to equal to this mass times your V over T. which is your velocity over your time. Let me go ahead and label this out. So this is our acceleration, which is going to be meters per second squared. This little fella is our mass, which is in kilograms. And this is your velocity, which is going to be in meters per second. And your time, which is going to be in your seconds. I like to write time in seconds. So it would not look like a 5. So basically, we're going to take this little fella and we plugged it over here. Let me go ahead. So your force is going to equal your velocity divided by your time. But what is time? Let me go ahead. What does the time equals to for an object that is moving? Well, we defined that the velocity, and let me actually go right back over there. We defined that the velocity as distance over time, which means from this case that the time is going to equal to your distance over velocity. Yeah. So we can go ahead and submit it over here. So our time is going to equal to our distance over velocity, which means that our force is going to equal to the mass times the velocity, the first velocity, divided by your time, which is we said it was gonna be your distance, times the second velocity, distance over v, dt over v, which is gonna equal to mv squared over d. Now, what's d? D is your displacement or your distance. Actually, let me do a different color. Again, we defined d as displacement or your distance. Now, what's the displacement? Well, we look over here. It is right this area, right over here. This link's right over here, which is called what? We call that R for radius, which is going to be in meters because it's defined as a distance. So we can actually come into our little equation and say this is going to be mv squared over R, free radius. And that gave us, ladies and gentlemen, our equation for the centripetal force, which is mv squared over R. So coming back to our little picture over here, each one of those, that's going to be your centripetal force pulling downwards. And this is going to equal to your mv squared over R, your mass times velocity squared divided by your radius. Now, notice there's 3 things that accumulate this equation. Your mass, which is your m, your velocity, and your radius. And notice that when the mass goes up, your, and let me go ahead and label it. We label centripetal force as FC. That means when our mass goes up, according to this equation, your centripetal force will go up. Our velocity will go, if the velocity goes up, that means your centripetal force goes up. If your radius goes up, that means your centripetal force will go down, and vice versa. When the mass goes down, centripetal force goes down. When the velocity goes down, your centripetal force goes down. When the radius goes down, you're going to have more centripetal force. It will go up. So the smaller the radius, the higher the force. And vice versa. The higher the velocity, the higher the force, your centripetal force, and vice versa. And the last one, the higher the mass, the higher the force, and vice versa. So we talk about centripetal force. We're talking about a center-seeking force as an inward force exerted on an object to keep it moving in a curved path, which is going to equal to mv squared over r, your mass times your speed, velocity squared, divided by your radius. Now, the greater the object the mass, the greater centripetal force, the faster the object moves, the greater centripetal force, the smaller the circle, the greater the centripetal force, and vice versa. So let's do a little example over here. Now, before we do example, I would like to go over my 4 rules. So Dr. Malek's 4 rules. And I'm going to put a circle around it because that's Dr. Malek's fantastic 4 rules. Number 1, write down the information. Number 2, something is going to equal you double question mark. Number 3, write down the equation. And number 4, like plug and play, I call this plug and solve. So let's take a look at our question over here. You got a 1,000 kilogram car traveling at 5 meters per second at 30 meters per second, at 30 meters radius. Turn. How much centripetal force do the tire have to supply? Well, our first piece of information over here is the mass. So using this one is our little example. Your mass is going to equal 1,000 kilograms. What else do we have? Our velocity is 5 meters per second. So your velocity is 5 meters per second. And then our 30 meters radius turn, that is our radius. So R equals 30 meters. And we are looking for your centripetal force. Now, use rule number 1, rule number 2, rule number 3. FC equals, write down the equation. FC equals mv squared over R, which is going to equal to 1,000 kilograms times your 5 meters squared divided by 30. So which means that your FC is going to equal to your 1,000 times 25 divided by 30. And if you plug it in, we should get 833 newtons. 833. Yep, 833 newtons. Let's do one more example, shall we? So you got a road hump Has a 12-meter radius. What is the minimum speed that the car will leave the road at the top of the pump? So the only information we have is the radius. So let me go ahead. Example 2. So our radius in this case is, how much we said? 12 meters. We don't have any other information. And what are we looking for? We are looking for the speed, the minimum speed. So we're looking for your speed. Now, you know that if it's going over a hump, that means your centripetal force is going to equal to mv squared over r. But we don't have the mass to calculate that. But you know that the F is going to equal to ma. And which ma? Let me actually rewrite that so you can put a different color. So we said that the centripetal force is going to equal to your mv squared over r, but it's a force that has to equal to mass times acceleration. Which acceleration? Gravity, which is, give it letter G, which is 9.8 meters per second squared. So in this case, we can see that mg is going to equal to mv squared over r. Cancel out the masses. So that will gives us G equals V squared over R, which means that your velocity is going to equal to the gravity times your radius, and it's going to be squared, which means that V is going to equal, and I'm going to organize it a little bit, it'd be RG. And in this case, it would be square root of 12 times 9.8. And if we plugged it in, we should get 10.8 meters per second. Yep, we got 10.8 meters per second. And that should conclude the definition of centripetal force. If you need anything, just you can email me at abunaemeh@gmail.com. Thank you so much. Have a nice day.